Hello, I'm Barry Shore, Professor Emeritus at the University of New Hampshire and Head of Content Development at SSGI. Improving process efficiency and quality can be challenging whether the improvement focuses on government or non-government organizations. What steps should be taken first? What steps should be next? What tools would be most appropriate, and how much resistance will be encountered? While these are not easy questions to answer and every situation is different, following the Lean Six Sigma methodology can be helpful. It has proven itself on many projects from small to large. Here is a case study that follows a step-by-step approach to using this methodology successfully. The Department of Transportation's approval process for contracts is lengthy. It often takes 4 or more months from start to finish. 1 month ago, Kyle Simpson, who was certified in Lean Six Sigma, was asked to lead a team to improve efficiency. The problem was that the average time to approve and process contracts for road repairs, infrastructure maintenance, and new construction projects was 130 days. This caused significant delays in starting a project, often leading to the erosion of goodwill with cities and towns in the state and higher costs due to inflationary pressures on contractors. Drawing from his experience in Lean Six Sigma, Simpson used the first team meeting to review the Domaic framework. It would guide the project. Define, measure, analyze, improve, and control. Define. Working with the team, the problem and the project's objectives were formalized. The project will address excessive contract processing time in the procurement process and reduce approval time from 130 to 60 days. To define the project further, they built a SIPOC diagram. It helped them identify suppliers, inputs, process steps, outputs, and customers. For example, under suppliers they included contractors, procurement staff, the legal department, the IT department, and state and local officials. It would ensure no variables would be ignored. Measure phase. In the second phase, measurements were taken to quantify the current state. Later, these measurements would be used to compare the results of the project. These measurements included process duration, or the time taken for each step in the process from bid solicitation to contract signing, volume of work, or the number of contracts processed monthly, and defects, instances of rejected or returned contracts due to errors or incomplete documentation. For example, here is data on the number of contracts processed over 10 months. The average number of contracts processed monthly was 72.3. Process mapping. In addition to process measurements, a value stream map was created. It documented the flow of steps from project approval to contract signing with the vendor. Here's a slightly more complex version, often called a process map, illustrating how a decision point can be added to the flow chart. Analyze phase. Root cause analysis. The focus then turned to determining the real cause behind delays. In Lean Six Sigma, the real cause is called the root cause. Here, every effort is made to move past a simple explanation that might focus only on symptoms, because addressing symptoms is unlikely to have a meaningful or long-lasting effect. So it is important to uncover the root cause. 8 wastes. In searching for the root cause, we often use the Lean Six Sigma concept of 8 wastes as a guide. Simpson's team identified the following subset of relevant wastes: transportation, too much movement of forms from one person and one department to another; waiting, excessive waiting between steps, over-processing, too many people engaged in steps that add little value to the approval process, defects, errors made by applicants and by office staff. Multivariate chart. The multivariate chart was one tool the team found helpful in better understanding the process's inefficiencies. It was used to explore the average time and range for each step in the process. Here are the processing times for the three major steps in the approval process: bidding, review, and approval. The second column includes the shortest time to complete a step. The third column includes the longest time, and the fourth is the average over this same period. Here's a multivariate chart displaying the shortest, longest, and average for each step. The chart shows that the bidding process has the widest range, while the range associated with the approval process is quite narrow. The review has the highest average. What is also apparent is that approval not only has the smallest range, but also the lowest average. Reducing the range for the bidding and review stages and lowering their averages could contribute to improving total process times. Meanwhile, the approval stage seemed to be doing well. However, some improvement could still be possible. Nonetheless, some useful lessons could be learned by examining the relative efficiency of the approval process more closely. Why were they more efficient? Fishbone diagrams. Fishbone diagrams are another useful tool for analyzing and decomposing a problem to better understand its root cause. In this situation, contract processing is the presenting problem, and as such, it becomes the head of the fish. From this diagram, we can see the major categories contributing to the problem include technology, processes, people, and environment. Below, on the horizontal lines, the issues are further decomposed in search of a root cause. XY matrix. The next step was to build an XY matrix. This matrix would help determine which controllable input variables would have the greatest impact on output. The controllable inputs were listed in the first column. They included manual paperwork processing, redundant steps, and bureaucratic culture. The outcomes were entered across the top. They included processing speed, constituent satisfaction, and compliance with state and federal requirements. The outputs are then ranked according to level of importance. For example, speed is very important, 9, but compliance, 5, is much less so. Subjective estimates are now made to reveal the extent of the relationship between inputs and outputs. For example, manual processing has a significant relationship to speed, 9, but very little relationship to compliance, 3. Finally, the subjective estimates are multiplied by the relative impact scores, and the results are entered into the last column. The analysis suggests that the most productive use of time should be directed at addressing manual processing. Failure mode and effects analysis, or FMEA. Before moving from the analysis phase, the team held an FMEA session. It would explore ways in which the system might fail. During a brainstorming session to address this issue, it was recommended that reasonable goals be established and that automated alerts be set to inform those doing the work that a deadline was approaching. Reaching Six Sigma. Simpson kept a Six Sigma goal in mind as the team moved closer to completion, but realized that setting a Six Sigma goal of fewer than 3.4 defects per million opportunities would be unrealistic and costly. Instead, a more realistic Four Sigma goal would be considered, where as many as 6,210 defects per million outcomes would be tolerated. Improve phase. Eliminate non-value added steps. The Lean Six Sigma team implemented the following changes. Digital workflow system. Introduced an electronic procurement system that automated bid submissions, approvals, and tracking. Streamlining approvals. Reduced number of sign-offs by delegating authority to department heads for low-value contracts. From the multivariate study, the biggest advantage would be to digitize the workflow. Control stage. Once a system has been improved, there's no guarantee that it will continue meeting expectations. So Simpson set up a system to collect data on completion times and plot results on a control chart. Notice that the sample means in this example are within the upper and lower control limits, so the permit process can be considered under control. Results. Here is a summary of the results soon after changes were made, staff trained, and the system implemented. Processing time. Average processing time dropped from 130 to 55 days. Error reduction. Rejected contractor submissions decreased by 65%. Cost savings. Projects started on time, avoiding inflation-driven cost increases estimated at $500,000 annually. Transparency. The digital workflow system improved visibility for all stakeholders, enhancing trust in the procurement process. Once became clear that the project was successful, Simpson commented, "The team did a great job, and I am confident that we can help others at the state level make processes more efficient. We should consider inefficiency at the Department of Motor Vehicles and the time job candidates wait after a job interview before being offered a job. Here is a situation where good candidates are long gone before a decision is reached." That's it, a brief introduction to how we can organize and manage a Lean Six Sigma project. While your project may involve other tools and is likely to go into greater depth, the basic format and direction described here can guide almost any Lean Six Sigma project in government. To recap the basic issues of a Lean Six Sigma study: follow a framework, clearly define the problem, measure the problem parameters by collecting data, displaying the data in charts such as fishbone diagrams, analyzing the data using such tools as multivariate charts and value stream maps, improve the problem, and finally control the process to ensure that it continues to meet goals. That's it. A brief step-by-step introduction to how you can apply the basic principles of Lean Six Sigma to government. For more information about our certifications, see the description below. Thanks for watching.